喂，可以听到吗？
可以的，老师。
啊，金红是吧？
对，
这个你知道这个分享怎么分享？我用的是iPad，怎么分享这个下载的一些文件？
老师不可以投屏吗？
我不知道怎么投啊，这个东西。行，它这个只有限的一些。能看到吗？金红
现在看不到。
，OK，还是看不到是吧？这个你们有知道这个iPad 怎么投屏吗？就是我看它那个文件夹是固定的呀，有 Dropbox 有那些，怎么投？我去试一下，我去别的会议室，我先试一下，这怎么投？你们先等一会儿，我先这个指定军火。Hello, can you hear me? Good evening, everyone. Junho, can you hear me?
Yes.
Can you see the shared slides?
Yes.
Okay, then we'll start. So, good evening, everyone. Today is our second lecture. So we will continue the first chapter of our dynamic programming and stochastic control course. It's about the finite horizon problem. Last time we have intro. Okay, so this is the outline of our today's lecture. So let me see. Okay, I can use pen. Yeah. Let me see if I can open in another. So first, in this lecture, we will continue to look at the basic problem, basic finite time horizon. Problem. After that, we will have an example. Okay, is a inventory example. We call it inventory problem. After that, we will introduce the principle of DP, dynamic programming. Principle and algorithm. Okay, and lastly, we will look at the example. Okay, this is called a linear dynamic system. Dynamical system example. Okay, in this example, we will apply a dynamic algorithm to solve the optimal controller. Okay, in this case, in both the deterministic case and the stochastic case. So let's go to the main results. The main no problem. Okay. Anybody know how to open the PDF here? It doesn't work well. I will reshare. So we will continue. So last time we introduced a basic problem. We introduced a discrete time dynamic system like this. Xk plus 1 equal to fx, a map fk, which maps xk and uk and wk to xk plus 1. Here k is a discrete time. We start from 0, k from 0 to n minus 1. Okay, so xk is the state of the dynamic system. It summarizes past information, and it's relevant for future optimization because xk will affect the evolution of xk plus 1. So it's summarized past information, and also this xk also affects the evolution of future states. So this is dynamic system. And then we have wk, omega k. Omega k is random parameter, or we call it the disturbance or noise, depending on the context. So here we assume the probability. So we know the probability distribution of wk. We know pk of the probability of wk given xk and uk, sorry, omega k. So this is our assumption. We assume given xk and uk, the action and the state, we will know the distribution of omega k. And omega k is not depend on, so given xk and uk, so the distribution of this guy will not depend on wk minus 1 ... to w0. It will not depend on the previous, the historical noise given xk and uk, because xk has summarized all past information. Given that, and the given uk, distribution of wk will be known. This is our assumption. Okay, with this assumption, actually we can apply dynamic programming principle to decompose a large scale DP problem into solving a series of small size subproblems. This is a very important assumption, because only with this condition we can decompose the whole problem into subproblems. So this is why we require this assumption. And next, I will introduce the parameter is uk. uk we call it control or action. Actually, in some literature we call it action. It's a decision to be selected at time k from a given set. So uk belongs to a set u xk. Okay, so this given set may be not a fixed set. This set may be depend on xk. So for some xk, this set may be large, but for some xk, this set may be small. So that reflects the fact that at different states, you have a flexible set of control or action to select. Okay, this set may not be a constant set. It's a it varies with respect to xk. Okay, this is the feasibility in the formulation. So alternatively, to describe this dynamic system, we can also use a probabilistic language. Okay, we can use the transition probability to describe the state dynamics if the state belongs to a finite set. So we can use this transition conveniently, okay, to give a probabilistic system description. Okay, so let's move to next stage. Okay, so okay, so I don't know how to use this app, so each time I will erase everything. So next definition I will introduce is policy. Policy is a list of function. Okay, the function I will introduce later, but remember this is a list of function, and from mu0 to mu n-1, so we call it pi. So each mu I is a function. Okay, it's map states into control action. Okay, so mu k is a map from xk to uk. So this is a map determines, given the state, which action we will choose. Okay, this is a map from state to action. So given this list of maps, we call it a policy. So this policy describes at each stage, when we are at stage k, so we are at state xk, what action we will choose. Okay, it is rule. Okay, describing which action we will use given xk. So that is why we call it a policy. Okay, so here pay attention to the notion. Okay, this is the policy is a sequence of maps. Okay, or mappings, not it is not control or action. Okay, it is a list of maps. Okay, mapping states into controls. Control is just output of this mapping. So this policy is a mapping. Okay, a set of mappings. So not a set of control signals. This mapping rules at each state which control you will choose. Okay, it's a relation between state and control. This pair. Okay, you pair them together. This is a policy. Next is cost function. Okay, here's cost function. Okay, another concept is admissible. Okay, policy. If for each mu for each state xk, and we have mu k xk belong to the set of available actions, controls, then we call this policy, this pi is admissible. Okay, admissible. This is the definition of admissible policy. So only admissible policy is feasible in practice because it belongs to the output of the map. Okay, belongs to all feasible the feasible control set. And next is cost function. Here in basic problem, our cost function is only allowed to be additive over time. At each time from k equals 0 to k minus 1, okay, we can apply a control, okay, into the dynamic systems. So in general, we can define a cost, okay, at each stage. This cost is a function of xk, the state, current state, and the uk, the control signal, okay, applied to the plant at time k, or the dynamic system at time k. At the same time, this cost may be a random variable, so it's a function of omega k. This is all the cost from k equal to 0 to n minus 1, capital N minus 1. And at last time, we also assume we have a terminal cost function. Okay, this terminal cost function, because we cannot apply control any longer, so this function is only a function of the state. We assume this is a deterministic one. So it consists of two parts. So from k equal to 0 to n minus 1, the cost is a function of xk, the state, the control, and the random noise. And the last stage, at stage n, okay, this is the terminal cost. So gn is special. It's only a function of xn. So this is the formula. Okay. If you don't have terminal cost, you just let gn equal to 0. Okay. So this is quite general problem setting. You can adapt different. You can adapt it to different problems by letting G taking different forms. Okay, so this is the cost, and next is optimal policy. Optimal policy, okay, as the name suggests, you can imagine this is the policy that minimize the total cost. Okay, this is the total if given if we are given so j pi 0, just we expectation, okay, of this gn xn terminal cost plus this cost jk xk. Here we are applying the policy pi. So here this u equals to mu k xk. Okay, because you know the pi is defined as a list of mapping. Okay, mu wk. And this is the average cost. Okay, given x0, given the initial state. Okay, so this is the cost given initial state and under a policy pi. So for optimal policy pi star, it means this is the minimizer of okay, of this cost. When pi belong to all, when pi is admissible policy, okay, overall admissible policy. This is the optimal policy. So here from the formally, this pi is function of x0. Okay, because x0, this j, okay, this objective function is function of x0. So formally, pi star should be a function of x star, means with different x star, x0, okay, we may have a different x star, literally, okay, from formally, okay, but we can prove later that actually this pi star is does not depend on x star. Different x star, okay, we have a uniform pi star. This is what we can derive from DP principle. But when we look at optimal cost function, okay, is the minimum value of this is equals to, this is equals to j pi star x0, okay. This is actually a function of x0. You have different initial state. Of course, you are expected to have different cost function, optimal cost function. Okay, in general, this optimal cost function is related to the x star, the initial state. Okay, this is something of introduction of to basic problem. So next we will introduce a concrete example of this basic problem. So let's remove everything first. Okay, this is called inventory problem. So in the inventory problem, we need to order a quantity of a certain item at a total period time n. Okay, so here k equal to 0 to n minus 1. In total, we have n periods. To meet a stochastic demand, so demand is from customers, but customers' arrival is a stochastic process. At the same time, we need to minimize the incurred expected cost, okay? Because the inventory problem, we have cost for ordering the items and also to store the items, we have some cost. And here, xk is a state, okay? Xk is a state, represent the storage, the stock available at the beginning of period k. Okay, and this is the xk, the available stock. And uk is the stock order at the beginning of period k, of k, let's say of k. And we assume if we order the item and we will have this item immediately delivered, okay? This happens in within very short time. So this is immediate delivery. And also we introduce this stochastic demand. During period k. Okay, and we know the distribution. Okay, if given x, given u, we know the distribution of omega k. Okay, this is assumption in the DP problem, and we will know that this xk is a scalar. This can be a continuous real variable, or it can take value from a discrete set. If we order, we can only order some fixed possible quantities of items. Then this actually will take value from discrete set. So the nature of this set may different from problem to problem, but we don't care too much about the structure of different specific problem, but we will extract the common characteristic of the problem and solve this kind of problem using DP algorithm. So DP algorithm rely on their common features, not the specific structure of different problems. Okay, so we will continue. Okay, we'll continue. Okay, let's review. Let's review this page. Okay, you will see the stock at next stage depends on the previous stock and the previous order and the previous demand in this way. Just the order will increase the quantities of the current stock, and the demand will consume your stock. Okay, if we have the demand is larger than the current stock, so in this case the demand will be backlogged. Okay, and will be filled as soon as stock is adequate. That means in this case the state can be negative. Negative means the demand is backlogged and will be fulfilled in the future by the future stock. Okay, when the stock is adequate, become positive, then it will immediately fulfill the previous demand. So here, for this reason, we can allow xk be a negative number. Okay, negative number means the demand is larger than the current stock, and the demand will be fulfilled in the future. Next, we will look at the cost. Okay, here we consider two costs from two parts. Okay, A, we have storage cost or shortage cost. Okay, here for the storage cost, xk is larger than 0. For the shortage cost, xk is smaller than 0. You can interpret this storage cost like the cost of the space, because you store something, you need space, you need to pay for the space. So when xk is larger than 0, so we storage costs will incur. And when xk is smaller than 0, here is larger than 0 or equal to 0. The customer demand cannot be fully satisfied. So in this case, we will have cost, okay, because that may if the customers will turn to buy other companies items. So in this case, we will lose the customers. The customer will outflow. So in this case, we will have shortage cost. The other type of cost is called you will pay for the order, okay, of the stock. So that will, in this case, there exists cost, okay. This cost is proportional to the quantities of order, okay. You ordered UK quantity of items, so this is the unit price times UK. Unit price is C, okay. This C is unit price. This is the cost. So in total, this defines the cost here, GK. Okay, so GK is a function. In general, it's function of XK, UK, and WK. So here XK is the storage. Okay, it will affect the cost, storage, and the shortage cost. And the UK will affect the cost B, okay, because the cost B is C times UK. And here, actually, this cost does not explicitly depend on WK, but XK is depend on omega k minus 1, omega k minus 2, and omega k minus 0. So in general, this GK still is random, and this is the cost at the last stage. Okay, so this is the whole cost. Oh, I'm sorry. This cost define the cost at the next stage. Okay, because here this characterize the storage and shortage cost at next xk plus 1, the next stage. Okay, this is the rxk. This part is rxk, and this part is cost E. This is the cost A. Okay, so this is the cost. And the next step, we will, after the cost defined and the system dynamic Okay, let's continue. Can you hear me? I switched to another computer because my iPad is run out of power, so I switched to my computer. But I cannot like last lecture, I cannot make notes. So we will look at slides, and I will try to explain the main idea. Okay, can you hear me?
Yes.
Yes. So having given the cost function defined, so next we will try to minimize the total cost over the n periods. So how to we minimize the total cost? So one method, okay, this is quite easy. You may think about it, quite easy. So imagine you can select all the orders at once at the beginning, okay, at time 0.
Professor,
can
we cannot see your screen.
Determine, okay, at time 0, at time 1 till time n-1. How many items you will order? Okay, this can be determined at once at time 0. We don't know how many customers will arrive at time 1, at time 2 in the future, but we just blindly determine, okay, the orders,
Professor,
in the future. Okay, this is open. We call it open loop policies. This is quite simple because you can you know the. Okay, I will share again. Can you see the screen? A PDF.
no, we can't.
Can you see it now? Oh yes. So let's continue. So the cost function, so in the open loop policies, this is quite simple. You just take expectation of all the, because you know the distribution of omega k. I just you take the expectation, and this becomes the total cost become the function of u0, u1, dot dot dot, until un-1. Okay, so this is you can use a nonlinear optimization problem algorithm to solve this problem. Or if you're lucky, if this linear is even simpler, okay, you can use linear programming to solve it. But the key point is that the feature of open loop policy is that you select all the u, okay, at once at zeros. So UK is just some minimizers, the minimizers of this objective. Objective just to take the expectation with respect to the all WK. Okay, and in contrast, you can do it in a much smarter way. You can postpone placing the order until the last possible moment k. Okay, at time k, when the current storage stock XK is known to you, then you choose UK. Okay, you postpone to determine, okay, the order until the last possible moment. Not like the open loop policy, you do it at once at the beginning of the dynamics. Okay, here you postpone your decision because there is no penalty for delaying your decision, your order up to time K. You are allowed to do so. It's free. But the difference is that now we know exactly the possible the current stock at each time step at the beginning of time K. Then you can adaptively choose your order to your stock. In this way, you can place order more accurately. Okay, if your stock is small, then you can order more items so that the customer's demand will be fulfilled. Okay, at the same time you have a smaller cost. Okay, so this is you can imagine, okay, the closed loop policy is performs better than open loop problem. Actually, this is true when we have the dynamics is a stochastic systems. If we determine we cannot take the advantage of information to get a smaller cost, because deterministic everything, the dynamics has been fixed. You can fully predict, okay, what's the future state, even at the beginning of the state. So there is no difference between making decision at once at the beginning of time K, or you postpone all your decision till the last possible moment. There's no difference because you have a predictable trajectory of the dynamic system as long as the initial state is given. Okay, but stochastic, you can gather more information when you postpone your decision, and you can take advantage of the information that become available. Okay, so this is the conceptually what's the difference between open loop and closed loop policy. So in the homework, we will assign a problem, okay, related to the comparison of the performance between open loop policy and closed loop policy. So, okay, so far so good. Any questions? Do you have any question so far? So next we will look. So if we choose closed loop optimization, closed loop policy, then you need to decide the rule, okay, the mapping from state to control. You have this mapping, means you have a policy to solve this inventory problem. So this is the policy consists of a sequence of this mu from mu 0 to mu n minus 1. Okay, the whole thing compose a policy. Okay, so here I have remarked that actually we are not interested in finding the optimal numerical value of the policy, but rather we want to find an optimal rule for selecting an action at each time period for each possible xk state. Okay, we're not interested in the numerical optimal value, but we are really interested in the process of finding the optimal rule given each possible xk. Okay, so here we need to know, given xk, how do you do, how many items you will order, so that in the future, okay, we can strike a balance of the favorable current cost, low cost, against the unfavorable, okay, unfavorable high cost in the future. So we must strike a balance between the future cost and current cost. So this is how we find the optimal rule, okay, for selecting the order. This is our interest in when we make a decision. So this is the dynamic programming. This is actually the so-called dynamic programming algorithm. We use this algorithm to solve, to give the optimal rule for selecting control actions at each time step, given each possible xk. So this is the introduction of our next topic, the principle of optimality. So we are interested the rule, okay? These rules, they forms a policy. If the rules they are optimal, then we will say this is optimal policy. So we denote it as x pi star. It consists of a sequence of mu I star, okay, from 0 to n-1. And also we consider at least tail subproblems. So in the tail subproblems, so we are not start from time 0, but here for the tail subproblem I, we start from time I. At time I, we are given at state xi. We start from xi, suppose. And we want to minimize the cost to go from time I to the end of the problem, time n. So this is the tail subproblem start from time I. So we k equals to I and to k equal to n-1. We sum up all the cost in this period, and finally we merge the cost with the terminal cost function gn. So this is the cost to go function. This is the cost of the total of the tail subproblems. Okay, this is tail subproblems, and correspondingly we have the toy policy. The toy policy is not the optimal policy of the tail problem, but it's a truncated version of the optimal policy, because we know we have a notation for the optimal policy, and we truncated the optimal policy from mu I-1. We remove the previous maps. We only keep the optimal map from mu equal to mu I equal from mu I to mu n-1. Okay, this is called tail policy. So far, we don't know what the relation between the tail subproblems and tail policy, because tail policy is generated from the optimal policy, but tail's problem is a truncated problem. We don't know whether the tail policy is still optimal policy of the tail subproblem or not. Okay, that is unknown. But the principle of optimality answer this question. It said the claim is that the tail policy is optimal for the tail subproblem. Okay, actually it's answered. The truncated optimal policy is also optimal to the tail subproblem. This is what a principle of optimality trying to say. And in other words, intuitively it means optimization of the future does not depend on what we did in the past. Okay. This is a truncation, okay? Does not depend on what we did in the past, means we can truncate the optimal policy. This resulting tail policy is still optimal for the tail subproblem. Okay, this is what does this sentence mean? Okay. From here, we can derive the DP algorithm. Actually, the DP algorithm first solve all the tail subproblems. It solves backwards. It solves first the smallest size problem, the final stage, only one stage problem. So this is the most the simplest problem. It first solve this tail subproblem, then it will move backwards. It solves, then it will solve the tail problem consists of the last two stages, and so on and so forth, until it includes the whole stage. Once it solves the tail subproblem for the whole stage, it means the DP algorithm actually it has solved the original finite horizon dynamic programming problem, finite horizon problem. It's run backwards. Use the solution of the tail subproblem of shorter time length to solve tail problems of longer time length. So it's moved backwards. So this is the procedure of the DP algorithm. And actually, this DP algorithm is developed based on the principle of optimality. This principle of optimality, we will show later in the proof, is guaranteed that the DP algorithm will give you, will output the optimal policy for the finite time horizon problem, for the original problem. Okay, so now following the DP algorithm, first we solve the smallest subproblems. Just this problem, the cost only have one stage cost, GNXN. Okay, here this is not controllable. Okay, because we at time stage n we don't apply any control. So this is trivially, this GNXN will be the optimal cost at the final stage. Okay, this is the trivial. Okay, and then we move backwards. We use, suppose we use JK plus 1. This cost is given. We have this is computed at the last step. We know what is it. Then at the current stage, we will use these known things, okay, to calculate JK in this way. JKXK is do the minimization. This minimization is try to solve the sub problem. Okay, sub problems. And this problem is solved for any given possible xk. So this equality, this step, it must be implemented for each possible xk. Okay, not only one feasible XK, but any possible XK. With this JK computed, then we can continue to iterate this process. We can get xk minus 1, xk minus 2, okay, until not xk, jk minus 1, jk minus 2, until j0. Once we obtain the value of j0 for x0 is equals to the optimal cost j star x0. Okay, why this is so? We will answer this in the proof. Why this j0 x0? This is generated from DP algorithm, but this j star x0 is defined to be the global optimal cost of the problem. So why these two quantities, they are equal? We'll prove it. And the next, the resulting policy, pi star, okay, pi star, this mu is solved iteratively in the previous iterative steps. We put them together, it forms the optimal policy. Okay, so DP algorithm that not only give us optimal cost function, but also gives us the optimal policy of the problem. So this is something about the computational complexity. Actually, we need all the tail subproblem to be solved. It's not only solve the original large size problem, but also it solve all tail subproblems with all possible time lengths from the final stage to the original problem. Okay, it solved much more problems than solving original problem. But in total, the DP algorithm, if you use brute force to solve DP algorithm, although you solve only one problem, but this problem has a quite large size, still, okay, the computational complexity is larger than solving a list of subproblems together. Okay, so the complexity of DP is larger than the complexity of the tail subproblems. And in terms of computational complexity for finite space problems, actually we will see that for the DP algorithm, if you use brute force to solve it, in general you will need the numbers of the control action, okay, to the power of the total time steps times the number of elements in the state space. Okay, this is a base to the power of the time periods and time the cardinality of the state space. So it's grow very fast. It will encounter the curse of dimensions. Okay, but for the DP algorithm, you will see this is just grows as a polynomial. The complexity is a polynomial of the size of the action space and the size of the state space and the size of the time periods. So this polynomial is much friendly in terms of computational complexity than the DP algorithm. Okay, so next we will prove the DP algorithm by induction. So I have we have we will use the proof. Okay, I write in the last year. Okay, to show you how we can prove it, because I cannot write anything at this stage. So I will show you the slides in the last year. Okay, how we prove it. First, we will denote a tail problem by pi k. Okay, pi k is the tail policy, a tail policy, and we will solve all the subproblems. Start from the subproblems of last stage. Let's say for k equal to n. So as we just seen, we just saw this jn xk directly is equals to this jn xn. Okay, here we cannot control anything, so the cost, okay, solved by the DP algorithm is just equal to the optimal cost. So jn star means the optimal cost. In the future, if we don't specify otherwise specifies, this star means optimality. Okay, j star means optimal optimal cost function. And then we'll prove it using induction. So we assume this jk minus 1 for xk plus 1 is just equal to the optimal policy jk plus 1 star. So this is optimal. This is solved from DP algorithm. There are different things. So, but we assume that these two things are equal. And we need to show from in induction that at the previous stage, jk will also equal to jk star at xk. Okay, for each xk, these two things will equal, means these two functions, they are identical to each other. So if we can show this case, that means for each k, this jk will equal to jk star. And also, of course, it holds for when
那个老师那边好像出了一点故障，然后老师说就是今天就先提前下课，然后我们下次再继续讲。